Yes.
Yes, it is. Okay. Okay, should I start or?
Yes.
Yeah. Yep. Okay, so before the break, we just introduced this class of models. So that's what we're going to using. So as I said, this model has a special property of this generalized conformal structure. And yet a different way to describe what a generalized structure is the following. If you consider the Yang-Mills coupling as if it was a field, and then and assign transformation properties, then this model, you can assign appropriate transformation properties so that this looks like it has a conformal invariance. Of course, it's not a field, so it's an underlying structure rather than a bona fide symmetry, but that has implications. And for example, if you look at the two-point function of the energy momentum tensor, then this generalized conformal structure means that the form of the correlator is the one I indicate over here. So the factor Q cubed is because the energy momentum has dimension 3 in 3 dimensions. So that would be the behavior of a conformal correlator that has dimension 3. The factor of m squared is because we're looking at the larger limit. And then the fact that the theory is not conformal, but it has generalized conformal structure means that you still allow a general function of the effective coupling constant. So the effective coupling constant is the Toft coupling, which is dimensionful, divided by the momentum. And depending on whether this coupling is large or small, which of course now depends on the momentum, this can be computed perturbatively or not. So whether this theory is weakly or strongly coupled is an issue of scales. It's not an issue of theory. So for this, with this expression, one can now explicitly do the analytic continuation we had earlier, that one. So you can see with this continuation, so n squared, so the continuation, let's put it here, q goes to minus iq, and then n goes to minus in. And we have the effective coupling, so n squared goes to minus n squared, and then g effective. I can see the factors of I cancel out. This goes to g effective, and then q cubed goes like to minus I q cubed, and then the prescription was to pick the imaginary part. So then delta r is, so I pick the imaginary part of B, it's q cubed divided by 16 pi square. Okay. So quite often through the years when I give this type of talks, people are kind of stuck into that step. So what my quantum field theory is such that this makes sense. These classes of theories, it's manifest. So you can do them without doing any computation. So this is the answer. And so now if I input in addition, sorry, I didn't put here. So now then we have n squared, q cubed, the q's cancel out. And then you can see from here already another nice feature. So in this case, the fact that the amplitudes are so small are controlled by the fact that you have 1 over n squared. So the Largian limit, I'm using Largian limit in the computation, but this is justified a posteriori because the data is going to tell me that n has to be very large. So now this is true for any theory, weakly coupled or strongly coupled, provided you have this generalized conformal structure. Now, if you have if the theory is perturbative, if the scale in which you look at the theory, this effective coupling is small, this means that this function here, we have a Taylor expansion around the origin. And this is the answer at the 2-loop order. So the first answer, the first contribution comes at 1 loop, because the energy momentum tensor is quadratic in the fields. So that if you did 1 loop, and then you have 2 loops. 2 loops, naively, you would expect only that term. So every loop is weighted by additional factor of G effective. But of course, theories have UV and IR divergences. And that's what produces this additional log piece. And in addition, there is this red part, which I will come back to it at the very end of the talk. So depending on the field content, you can have infrared divergences. So there is an additional constant here, which will play a role further down the line. Now for comparison, so if you have a quantum field theory, which is not this type of generalized conformal structure, but rather it's a conformal field theory, a model which is more akin to inflation, which is perturbed by a nearly marginal operator, then this F would take that form. So if delta is close to 3, then this would give us the tilt. So this is the deviation for exact scale invariance in that case is controlled by how close is the deforming operator from being marginal. Yes, actually you will see this is exactly what happens. But,
so Kostas, is the claim that if you have the full field theory description is given by some renormalizable thing, or it could be some effective field theory?
I think the claim is that the full evolution would be given by some normalizable, some theory that makes sense in the UV, some normalizable theory.
Also string theory, not necessarily field theory.
No, it would be it would be field theory, because that's a holographic, 3-dimensional quantum field theory. Not the string. The string theory contains gravity as well.
Oh, okay.
Yeah. Okay, so again, in an alternative version of this lectures, we would have spent 1 lecture on this case. Is this? Yes. What happened here?
So just no.
So because it's not doesn't display the entire. But why? Yes. Yeah, now it shows. Let's go to the previous one. Yeah, so we go back here, we discussed this. So the fact that we have a nearly scalar invariant spectrum, this means that this function here should be nearly constant. And there are 2 different ways. Well, the 2 different models gives you different ways where that function is nearly constant. The one case is through perturbation theory. So at leading order, this is just a constant. So this is, in a sense, a new mechanism to generate a scale invariant spectrum, which only relies on the fact that the energy momentum tensor has dimension 3. It doesn't rely on conformal symmetry. So here, we got this behavior here. This Q cubed came from the fact that the energy momentum tensor in 3 dimensions has dimension 3. And this Q cubed cancels this Q cubed in the formula. Then at 1 loop order, the coupling constant always cancels out. So the coupling constant is independent of anything. It depends only on the constants, how many scalars, fermions you have, not on the coupling constant. So this is constant. So provided, so this is constant to leading order. So that's one mechanism to get scale invariant spectrum. And then the loop corrections give you the violation away from scale invariance. Now, if you have a CFT, something which is nearly CFT, like in the case of de Sitter, then the mechanism is different. So now in that case, you have a CFT. If it's exactly a CFT, would be exactly de Sitter, no inflation. So you need an additional, you need the analog of the inflaton, and the analog of the inflaton is a scalar operator, like the standard dictionary. Scalar fields in the bulk corresponds to scalar operators. So then you need the scalar field to drive you away from de Sitter. So it has to be relevant, and to describe inflation, it has to be nearly marginal. So if it is nearly marginal, the fact that this is nearly constant means delta is nearly marginal, and that's what gives you conventional inflation. Now we can start from that and work out the implications for the power spectrum and the non-Gaussianities by doing conformal perturbation theory, using this as a small number. And that exactly reproduces all results that Maldacena had in his 2002 paper, where he computes the non-Gaussianity.
So pure de Sitter is just exactly marginal.
Pure de Sitter is a CFT. So if you have an exactly marginal, it would remain de Sitter. So you need something which is marginally relevant to drive away to get slow roll. So the slow roll parameter is the difference away from the marginality. Okay. So now, universal prediction. So for all of these models, predict a spectrum, scalar spectrum, which is of this form. So you should contrast this to the kind of usual. So let's put it. So for inflation, you have something like this. So it's a monomial raised to power. Or for these models, you see it's 1 over 1 plus 1 over q log q. So here, when you have slow roll in inflation, the so-called running of NS is of the order of the slow parameter. And if you do running for running, is of order epsilon square, and so on. And this is the reason that when the Planck team fits the data to fits lambda CDM to data, they assume that NS is nearly constant. Or, they allow for first order corrections, but not high order corrections. So the theoretical motivation is that slow roll models of inflation have that property. So you don't expect to have this. Now, these models here are the exact opposite. So in these models, NS minus 1 is of the same order as alpha S, is the same order as dd log q of fs, and so on, wall orders. So these are qualitatively different models. So to compare those models to data, you cannot just open Planck. That's what we first did in 2009. But quite quickly, we realized you cannot really use Planck. And also, you would see in the abstract, there's no evidence for running. And we already knew from the beginning that there's as much running as there's deviation from scale invariance. And in the beginning, we look at the error bars, and the error bars were big enough to be of that size. Then WMAP came, they constrained more, but then it then became clear we really need a custom fit of this to data. And that's what we did. And then that showed that this model was, WMAP was competitive to lambda CDM, but still the error bars of WMAP were big enough to be of the size of the running. So at the time, we thought when Planck comes in line, or the data, which would reduce the error on alpha S by a factor of 100, that should rule out these models. That's what we thought. But then Planck came along, and you saw the fit in the beginning.
So have in mind a single field inflation type?
Yeah, so this is an analog of a single field because it.
They put in some
Well, I mean, this requires that the spectrum of the quantum field theory has few low operators with low-lying dimension. I mean, I also worked out multi-field. You can do multi-field as well. So the other universal prediction is that the tensors are also of the same type, not of this type. And finally, the non-Gaussianities are very, very, very special. So they have no local non-Gaussianity. Okay, I'm not sure how many of you are familiar with this terminology, but local is, in a sense, the most usual type of non-Gaussianity. So if tomorrow there is a measure of non-Gaussianity, of local non-Gaussianity of any value, that would automatically rule out these models completely. There's no fix. It's not like I can tweak it, maybe change some coupling and so on. That would fix. Secondly, these models, they predominantly always contain what is called exactly factorizable equilateral shape. Now, the equilateral shape is, when you do non-Gaussianities, you look at the sky, you pick any 3 points, and you see the correlation between the temperature. So equilateral is when these 3 points are on an equilateral triangle. Now, to be able to measure, this is the size of this, from the data, because they have 3 different data, if the power spectrum has a generic form, which is equilateral, it's computationally very expensive because they have to do many integrals numerically. So very early on, they found that there is a very special equilateral shape, which they call exactly factorizable. This is just kind of observational people, not theorists. And I said, let's use that to do the measurement because any other shape would be close to that one. Now, it turns out that model gives exactly that shape that they cook out just for the purpose of fitting the data. So when Planck got the value of FNL equilateral is literally for that model because there's no other model, there's no gravity model that gives that shape exactly. But now this model has an FNL, which is a pure number. It's 5/36, independent of any details. How many scalars you have, what is the n, it is completely, it's a pure number. And it could have been 5, it could have been, the fact that it comes to be 5/36 comes from a computation. But again, if, now there are bounds, of course, in FNL, this is within the bounds. But if they measure again tomorrow and they find it 5, again, that would rule out again all of. So these models are really very, very falsifiable in the entire class. And then it has an additional component, the orthogonal component, which depends on the non-minimal coupling. Okay, I'm not going to. So that you can, in a sense, suppose they find, again, the observer, I will discuss a little bit this non-minimality parameter in a minute, but this depends on, this is fixed by comparing with a number of tensors. Suppose they find tensors, and they observe non-Gaussianity orthogonal. Again, if the relation is not exactly what this class of models predicts, that would also rule out this model. So these are not models that you have qualitative, you have quantitative physics, and they're very falsifiable with something that should come along in the next 5 to 10 years. Okay, so now the results a little bit more quantitative. Yes. Now, in this case, it doesn't have an IR divergences. No. Okay, so the fit to data implies this G effective is very small for all the scalars seen in CMB. Again, the fact whether the theory is perturbative or not is a question of scales. And the scales we see in CMB is L from, let's say, 2 to 2000. It starts with about 10 to minus 4 at very high Ls, and it becomes of order 1 around L equals 30, so in this insert. So this means that the model becomes non-perturbative, and one can not trust the formula I just gave you in that region. So now if you use the model in the region, which is theoretically well-defined, L greater than 30, then the chi-square for the fit is what is given over here. So it's slightly smaller for holographic cosmology, but I mean, that just means they're less than 1 sigma apart. So it's slightly better, but less than 1 sigma apart. And then one can use that to discriminate between models. So as I said earlier, as UN gauge theory coupled to terminus only is ruled out. A model which is ruled in is as UN gauge theory with n5 non-minimal scalars with phi to the 4 interaction. Non-minimal means that the energy momentum tensor has the usual form plus an additional, this is the contribution for the gauge fields, this is the contribution, the standard contribution for the scalars, but has an additional piece that comes with the parameter. So this term is sometimes called improvement term. And if psi would be equal to exactly 1/8, the scalars would be conformal scalars. But in general, this is a parameter of the theory. So psi is a new parameter, is a non-minimality parameter. So all observational and theoretical constraints can be satisfied by choosing these 4 numbers. Actually, lambda doesn't really play much of a role. What is crucial is that you have psi and the number of scalars.
Right, so since here there's no analog of double scaling or anything like that,
just fit these parameters, yes, yeah. There's nothing, there's no other step. So I already gave you a formula for the power spectrum, and I compare with gravity. And then in comparison, the fit was good, equally good as lambda CDM. And then given that data, I can say which of my microscopic models can give the values that came out of the fit with the data. So the data.
No, I understand that. So there's no sense of being strong in this case.
No, there is a sense, because if this is small, then gravity would be strong. So when this is very, very small, then gravity is strong, and so.
But here they don't, some of the parameters because of Q.
Yes. But I mean, that's part of the story. Yes, it is. Depends on the scales.
I have a question. So why they cannot have interactions between scalars? Why it has to be?
You can have interactions between the scalars. You have phi to the 4.
But if you have 2 scalars, they can also interact.
Yes, but it is true. You can have more general models, which you have, instead of having, let's say, all of the same type. This is the most economic fit is to choose a large number of scalars, which all of them are of the same type, and they can interact with themselves. But the simplest option is to have a diagonal kind of coupling.
Then one more question.
But I mean, this universal predictions would hold for all models with arbitrary interaction, provided it's all phi to the 4 and they're massless. So they're not gonna, the data are not gonna discriminate between the 2. You need more detail. Yes.
Most species of scalars, there must be a collective, I mean, you get something like phi, phi j, phi k, phi l.
Yeah, you can do that. Yes. So that would be the simplest class. Yes. Yeah, that's an important term. Because that term here does contribute to the 2-point function of the energy momentum tensor, and therefore contributes to the formula for the power spectrum. No, you cannot remove this by Fourier definition. That, if you wish, this comes from a new term you can add to the action I described when you put it on a curvature. So it would be R phi square term.
Okay, that one. So there is some additional concept, maybe you're going to talk about it, is that you want the theory to be strongly coupled at some particular scale. Otherwise, you will not go to something like
Yes. So that this was the issue that I was describing here. I want the theory to transition from weakly coupled because this theory is super normalizable. This means it's asymptotically free because we're in 3 dimensions. So as you drive the coupling, as you move to the future or in the UV, the theory becomes free. But clearly, that's not what we want. We want a transition to a strongly coupled theory. So you need to modify the theory in the UV. And one way to do this is by putting this 5⁶ coupling. After you do this, then the theory now starts running, the coupling starts running. And then the hope is that now it would become strongly coupled, and then it would transition into that hasn't been modeled.
No, what I'm saying is, suppose the UV's theory is strongly coupled, it might have a local description in terms of completely different kinds of fields.
Yes.
And in that case, in principle, you can of course have more, like a lot of couplings, because there is a lot of fine tuning that you have to do. It's not obvious that you can have only one. I mean, that is to make this transition.
Yeah, so you may need to have more. I mean, again, it's building this reheating phase is an open issue. As with toy models, I think one first tries to build it in the simplest possible way, and then plays with it to kind of make a complete story. I think for me, it's still. I mean, again, I have one toy model where I can see the beta function emerging, but I don't have a complete model in the sense that I can really see it. I can perturbatively compute in the correction of the 5⁶. And then there is a competition between how small is that parameter with how far I can go to the future. So I think when it's slightly different strategy, maybe making an educated guess about what is the theory and see that that theory emerges in the IR, in which case you will have a control over analyzing the theory here rather than try to go up.
If it was supersymmetric, you could have probably taken help of cyber.
Yeah, so if it would be supersymmetric, yes. Yeah, there is one paper by Horacio Nastase where he tries to put supersymmetry. I think it's maybe a little bit early. So some parts are a little bit strong there, claims, but it is an interesting thing to do, yes. Yeah. I mean, straight supersymmetry with, you would say, why don't you put a D2 brane? That wouldn't fit the data, does have enough scalars. But one could try to put more general n = 1, and I think that's what Horacio is doing. But this still needs to be developed a bit more. Okay, so in a sense, that's where we are in a general case. The data justify the perturbative treatment, but also tell us that in this region, the system becomes non-perturbative. And that's what leads us to the next topic, which is lattice holographic cosmology. So if we want to compare to really fit all data, we need a non-perturbative computation at the very low L's. And for that, one is to go non-perturbative. And more generally, so here, using perturbation theory, I can model a universe which is very quantum. And if we use Einstein gravity, we model a universe which is very weakly coupled. And clearly, these are two extremes. Why nature would choose what we can calculate? It can be nature may not be as kind to us, maybe somewhere in between, where the couplings are intermediate. And if you have a method to compute non-perturbatively, you will have access to these models. And as you will see in the next few slides, this next model I will introduce sits here. It's extremely simple. And so far, it does seem to do quite well with the data as well. So what is this model? This is the simplest thing you can think of. A single scalar, no gauge fields. And in the adjoint phase U1. Okay. So what can be simpler? You just have a huge matrix. And you try to describe all of the very early universe with one matrix that has a 5⁴ interaction. And the energy momentum is this. Again, it's crucial that one has this non-minimality parameter. The two loops, this is something, the previous computation really needed people that had expertise in doing loops for phenomenology. That's why I started working with Coriano and De La Rosa. I mean, they're just a phenomenologist, and they have all kinds of codes to do this integrals. This model is something that you give as an exercise after QFT1 to do 2 loops. And okay, this is the answer in terms of the F. So there is a 1-loop answer, and there is a 2-loop answer. One of the coefficients turns out to be 0. Well, the n was the over, so that's in the large n limit. Actually, this, in the paper, we give it for finite n because it's simple enough. You can do it exactly, you don't need large n. But here I will use it in a large n. So the f's are the same f's you can see here. I had this expression here. So the 2 point is n squared q cubed, and then there was this function of f. And then I just gave you f naught. The f1 was 0, so the log term turns out to be 0 in this case, and the f2 is not 0. Okay, that's the model. Now it turns out in 3 dimensions, and for this model, and without the Yang-Mills, one can scale away lambda as well. It's a simple exercise. No, just this. Just this. Just this.
That's the difference.
Yes, with the previous one. Yes, just the scalar. I still want to focus on the singlet sector. I'm not discussing how to theoretically impose the singlet constraint, but okay, that's this is the model, and I'm just looking at 2-point function.
Why is zeta? Why is the xi?
I'll use in the next slide. So again, lambda can be scaled away. So the model really has 2 parameters. One is the rank of the gauge group, how big are the matrices, and second is the non-minimality. So the n is related to the smallness of the amplitude of perturbation that we saw earlier, and psi is related to the tensor to scalar ratio via this formula. So if psi would be 0, then you have you will need an enormous amount of tensors. So you need psi because we haven't seen tensors yet. And the fact that we haven't seen tensors yet means that psi is very close to be 1/8.
The conformal scalar point was what was the xi value?
So the 1/8.
1/8. Okay.
So if I put conformal scalars, then I will have 0 scale. So suppose we do not see any tensors. Right? That's a theoretical possibility. This would mean that this model will still be okay. It would mean that it's exactly conformal scalars.
But you're at least near the conformal scalar point is what to say.
Yes, yeah, this puts you near the conformal scalar.
R is small, this bounds are.
Yes, yes. R is now smaller than 0.05. So this means psi is close to an 8 up to to 100% up to 0.05.
Okay, I have a question. So normally you add the improvement term, but the gravity, the metric usually couples to the usual Pij, right? Not to the.
No. If you so there is a class of theories because I can introduce an R square, R phi square term.
Okay.
And that's from where that term comes from.
Okay.
Yes.
Okay, so you have to use this extra.
Yes, exactly. Okay, so how does this model do with the data? Okay, that's now the graph, the same graph I showed you earlier with this model. Now, if you look up here, okay, there are 2 curves here. There's a blue, which is lambda CDM, and there's red, which is the new model. And okay, we can't really see it, but I mean, it sort of blows up here. So it's really not doing very well over there. And this is the graph with the residuals. Again, it's not doing that well, but I mean, the curve does go down over there. And if you do it now quantitatively, so you want to check for which part of the spectrum the G effective is small. So the G effective becomes a further 1 around L equals to 60. So L equals to 60 is about here. So from here and above, the coupling constant is small enough, so we can trust this 2-loop approximation. But from here and below, we cannot trust this 2-loop result. You need a kind of lattice version of it. And in the region where you can trust the model, 2 6 and above, this model actually is 2 sigma better than lambda CDM. So now suppose the same continues for low L's, then it really becomes significant. It's not just doing the same. It's already 2 sigma. It started to say something might be there. Of course, we're missing, this is the big, at this point, we're still missing the most accurate data, which is the first peak. And to describe the first peak, when it's the spectrum at low L's. Okay, so again, it's to do that, one needs to describe the low L region, in its lattice methods. And another reason to discuss lattice methods is because of this infrared singularities, which I will describe in a minute. So in holographic cosmology, as I said in the beginning, time evolution is the inverse of renormalization group flow, which means that the initial singularity is now mapped to the infrared of the quantum field theory. And as I will show you in a minute, naively, the quantum field theory has an infrared singularity, which would be the image of the bulk initial singularity. But when you look at the theory non-perturbatively the infrared finite, which would be the resolution of the initial singularity. So we spent quite some time describing that. Okay, singularity. So this was this was a massless supernormalizable theory, and it has been known for a very long time that these theories have severe infrared singularities in perturbation theory. So when you have a supernormalizable theory, then you can see by power counting that the theory is well behaved in the UV, but exactly the same power counting tells you that the theory is very badly behaved in the IR. And if these infrared singularities persist non-perturbatively, the theory is just non-predictive. So anything, no matter how small is the coupling constant, the theory still is non-predictive because you have kind of information coming in from the infrared singularity. So, yeah. So yes. So we're gonna come to this. In the sense, when we did the computation, we used the conjecture of these people. This is for all theories of the type I have been describing. And the papers that they wrote, I mean, Jakiv, Templeton, and Appelquist, and Pisatsky, were for the same class of theories. So three-dimensional quantum field theories with Yang-Mills coupled to scalars and fermions. Yes. Well, what I will argue here is that this mechanism that they describe here is realized. What exactly happens in the AR, we don't really know even today. What we know is infrared finite, but we don't know exactly, does it develop a mass gap? Is it further down the line there is a fixed point? That really depends on the details of the theory. I mean, I could have another example of the same theory is ON model, 3 dimensions. Of course, we know that theory is a CFT in the IR. Another theory from that class is just Yang-Mills of 3 dimensions, and we know that theory develops a mass gap. So that's a question that depends on which theory we're considering. The gauge fields were dynamical, yes. Well, because the theories behave in a different way at different energy scales, and then the proposal was that this theory described the energy scales which we see in the sky. What happens before that or after is still to be. No, that's not true, because in some of the cosmologists try to come up with the models to kind of fix this dip in the spectrum for low L's that they described earlier, the large angle anomalies. And some of them are. Now, so some models that they describe was, and they just cut off the spectrum at some scale. And that cutoff could be the mass scale you generate dynamically from the Young mills. That would be one model. At this point, in a sense, I'm agnostic of exactly what happens at very low L's. But I say if the proposal is that this type of theory is... Yes.
Does large N help in making it simpler?
It does help, yes, because large N always helps with commutations. It doesn't help as much as with the ON models. We can actually solve them because this is this is a matrix model. You know, it says UN, so it just tells that you get planar diagrams. This is still complicated.
Exactly what observables you are talking about?
You will see. I will describe this. Yes, that's the next 5-10 slides. So, well, actually, what time?
We have
yeah. Okay.
10 minutes.
Yeah, let's see how far we go. Yeah. Okay. So the proposal was that non-perturbatively, I mean, the theory has a dimensional parameter, the Yangian's coupling, and non-perturbatively, this acts effectively as an IR regulator. Or to say it perhaps more precisely, I mean, they had specific models where you start and you see the theory has an infrared singularity. Then you put an explicit IR cutoff, you compute the observable. And then the toy example, they could actually solve the model analytically. And then tune the coupling so that it's perturbative and expand it. And then you would see that we had exactly the same as the perturbative answers. But now the IR cutoff was replaced by the coupling constant. Okay, that's what they would see. And I think these papers have over 500 citations each. They're well-known papers, but at the same time, I don't think anyone has one beyond the examples they discuss. In the sense, the papers were referred, but they haven't further developed. And I think we're probably the first to give kind of a new proof for a class of models where this mechanism is at work. Okay, so what does one need to do? There's a long list of things to do. So if you want to put a theory on a lattice, you need to discretize the model. That's run-of-the-mill, it's standard. Then you need to find the so-called massless point, which I will discuss. So usually in a continuum, there are some things we take for granted. We say we want a massless model, you write the Lagrangian with no mass term, and that's the end of the story. On the lattice, this is highly non-trivial because, of course, you put the theory on the lattice. What you want is when you tune, you go to the continuum limit, you want to have a massless model. But the mass term could be generated. You have to fine-tune so that you get a massless model. And then you want to find the energy momentum tensor. Again, at the continuum, this is straightforward. You say there are many different ways, but you say I put the theory on a Kerth manifold, I differentiate with respect to the metric, that's the energy momentum tensor. But the energy momentum tensor, as we also discussed yesterday, generates transformations. Let's say translations. It is the nether current for translations. But on a lattice, you have broken translations. So this means it's not conserved anymore. And this also means it mixes with other operators, either normalization group flow. And you have to find exactly the right mix, which would be conserved in the continuum.
You would also find the Xi parameter.
The Xi is not so hard because that's conserved already on the lattice side, already at the lattice level. Because that's, in a sense, identically conserved, where the other terms are conserved using the equations of motion. Yes. And then once you have that, then you need to compute the two-point function, which is, again, highly non-trivial. On the lattice, you need a lot of statistics. And then finally, compare with data, and you either declare victory or you say this model is not good. And then you do something else. Okay, so since we don't have much time, yeah, that's the discretization. So here, as I said, finding the massless point is non-trivial. So usually what one does is introduces a mass and then fine-tunes the parameters so that when you go to the continuum limit, this term disappears. And this is about this second point. So discretized continuum model is straightforward. So how do we do this? Okay, so what we need to do is, as I said, we need to deduce a bare mass and fine-tune its value so that the model becomes massless in the continuum. But how are we going to find this value to fine-tune? Now, you can start by doing this in perturbation theory, lattice perturbation theory. You put it here in a lattice, and you treat it perturbatively. So it's another regulator. I mean, we discussed a lot about regulators in the last two lectures. Another regulator is just to put it here in the lattice. And you can do that. So in perturbation theory, this critical mass is UV divergent up to 2 loops, and it's IR divergent starting from 2 loops. So this is the general form in perturbation theory. So A is the lattice spacing. So A going to 0 is removes the regulator. So that's the UV regulator. So that's the 1 loop term. At 1 loop, you have a log divergence, but you also have an IR divergence. Here I put an explicit IR regulator. And then at high orders, you have power law IR divergences. And the constants M1, M2, and so on depend on depend on N and the field content of the theory. So now from here, you can see that this quantity is still defined unless you can cure the IR divergences. And if there are IR divergences, and this formula doesn't make sense, then the massless point doesn't exist. So the theory I started from is, the theory I wanted to use belongs to the dustbin of theories, the swampland of theories. So for this theory to exist, this has to exist non-perturbatively. So then on a lattice, now the task is to compute that quantity non-perturbatively. And then to go back to the IR finiteness, the question is, so here this is a perturbative formula. What does this become if that object is non-zero non-perturbative? Is this the coupling constant, like Jakiv and others were suggesting, or is there something else? Okay, so again, UV infinities can be dealt with the usual mass counter term. There's no issue there. But unless the IR infinity is cancelled, then the critical theory doesn't exist. And the conjecture is that of this guys is that if this is correct, then the IR should be proportional to the coupling constant. If it is proportional, you can see all these higher loop terms just become a constant. And this becomes the log of the type I was describing earlier. Okay, to find the massless points non-perturbatively, there is a method which is called Bieder cumulant, and uses the following fact. So you have a phi to the 4th theory. If the mass is positive, then you have a kind of potential where you're sitting at a symmetric point of the theory. So this means the expectation values of operators like this one are going to be 0. On the other hand, if the mass is negative, then you have spontaneous symmetry baking, and this means that expectation values of operators will now be non-zero. So then what you want to see is you want to scan the values of M such that you go from positive to negative, and you see the transition in the expectation values. And to see whether there is a transition, what one computes is one computes this ratio here, which is called the Bieder cumulant. And okay, that's what we find. So in the continuum, that would be a theta function, so it would be like this. And in finite volume, finite size effects kind of smoothen the curve like this. So here we did n equals 2, that's the SU2 theory, n equals 4 is the SU4 theory. And we also done SU3 and SU5. And you can see, and then you can compute the asymptotics analytically. That's exactly, you get exactly the right asymptotics here and there. And you can also see there is a transition. Yeah, so I had a few other slides where I describe the approach to the criticality, and one can also compute critical exponents and convince yourself there is scaling behavior. But I think we're almost out of time, so I remove them. But if people want to see them, I'll be happy to show you. So we show that both of these models there is a scaling behavior. So we do find that this mass non-perturbatively, and now one can ask, given this mass, what can you tell about the model? Is it IR finite or not? And to answer that question, we use Bayesian arguments. So if you're on a lattice, so the lattice put the theory in a box. Because if you put the theory in a box, the box introduces automatically an infrared regulator. So it's not surprising that we get finite answers. The question is what happens if you try to remove the box? So then we define model 1, which is, it says what we want, so to speak, where G acts as an infrared regulator. So if model 1 is preferred by the data, this means we have infrared finiteness in the continuum. And then model 2 is that the size of the lattice acts as an infrared regulator. And if that would be the case, then you get infrared divergences in the continuum limit.
In the previous model, G acted in the 2-point function computation of P.
Yes.
So the G already acted as IR regulator. Like the FI model with the time.
So I had this red term where I had G divided by G Yang-Mills. Yes. So in that case, when we did the computation, we had an infrared divergence, and then we assumed the mechanism would be correct, and we substituted for mu IR, G effective, and that removed that term. Yes. That would fit with this, in the sense now we justify that step a posteriori. Okay, so we have two models, and then we need to, I mean, this is a very busy diagram, and I think I'm only going to describe. So in the community is sometimes divided between using Bayesian analysis, where you have priors and so on, and kind of the frequentist approach, where you look at kind of chi-square. And we wanted to satisfy both camps, so we did both analysis. So that's the left axis. So the Bayesian analysis asks the question you want to ask. Given the data, which model is preferred? But to answer that question, you need to also input priors, which means what is the belief for the model before the data? And of course, sometimes the answer depends on your prior belief. And people do not like this and say, oh, you can influence the answer by your beliefs, which is true. At the same time, we can judge, in a sense, whether the physics input we inputted is right or not, right? So then, given that input, you get a definite output. While the other, the frequentist approach answers a slightly different question. It says, given the model, what is the probability for the data? And I mean, clearly, if the probability for the data is very high for a given model, that's a preferred model. But it doesn't directly ask the right question. So in this diagram, so the left axis are, in a sense, the probability of the data given the data. The right axis and the color is about the Bayesian evidence. I will describe a little bit more the Bayesian evidence. So now the Bayesian evidence is a quantity you can compute, and then here I color code the results. So if the answer for this quantity E is between in this pink region, then you would say both models are equally good. The data cannot tell you whether one is preferred over the other. If the answer is in this yellow part, then you would say there is strong evidence for one model over the other. And if the answer turns out to be in this blue region, if it is on the top, it would be decisive evidence for model 1. If it is on the lower part, you would say significant evidence for model 2. If you want to put it in the kind of particle detection language, we usually say we need 5 sigma to be sure the effect is there. So 5 sigma in this graph would be somewhere around here, just a little bit above the yellow line, roughly speaking. Okay, so now here, the circles indicate evidence for model 1. And you can see it's not, I mean, if you put it with sigmas, it would be, thousands, thousands of sigma. So I think this computation here is beyond any doubt that this model is infrared finite. If we believe that Higgs has been discovered, then you have to, in a sense, multiply this by this belief by hundreds of thousands. So how much you should believe that graph. So definitely, for this model, the mechanism, and then the mechanism is exactly what they described. So the coupling constant acts as an infrared regulator, and this resolves the infrared problems. Okay, so now we, in a sense, we found the massless point. The next task is to find the energy momentum tensor. I'm gonna skip this. Again, it mixes actually in 3 dimensions. For this model, it turns out it only mixes with one operator, which you can fix by demanding the Ward identity is satisfied in the continuum. We've done this in 2 different ways to determine that value, so we know that. And then what we're currently is to compute the 2-point function. There are 2 main complications. One is because the energy momentum tensor is a composite operator, its 2-point function has new infinities. Now, which some of them actually we discussed yesterday in the CFT discussion. In the continuum limit, you know exactly how to deal with them because you cannot account the term that depends on the curvature. But of course, on the lattice, you cannot do any of this. The lattice is flat torus. So you have to find a different way to remove the infinity. And we have devised a new method to normalize 2-point functions. And that's in progress. And then when it's enough statistics. So once we have this, we'll see whether this fits better or worse. But we've done in the past kind of an easier case. Rather than the 2-point function of the energy momentum tensor, we just did the 2-point function of phi squared. And then you can see how it goes. I mean, this is the perturbation theory in 1 loop. This is 2 loops. And then non-perturbative. This is what you get. You get somewhere in between. So this is 1 over G effective. So moving to the right is perturbation theory, and you can see data, the lattice data agree extremely well with perturbation theory. The arrow bars here, which you cannot see because they're very small. And then this is the non-perturbative region. This is the region we want to use for the data. So provided we can completely resolve these issues with normalization and so on, we have enough, this should give enough accuracy to be able to test. So that's where we are.
NL is the number of lattice sites?
N is which SUN you were doing.
NL is the number of lattice sites.
NL is the number of lattice sites. Yeah, we go up to.
And A is the lattice spacing.
And L is the lattice spacing, yes. And then AM is kind of the critical mass.
What is it? A critical mass.
And AG, so G is a dimensional parameter. So then G in units of lattice spacing is the coupling constant and lattice spacing.
So for different G's, you have different critical mass.
Yes. Okay, so now let me just quickly recap and conclude. I think perhaps the main thing I want to get across is really mostly this first point, that holography offers a unified framework for discussing early universe cosmology. Strongly coupled quantum field theories would give conventional inflation, and weak interactive or intermediate coupling would give new non-geometric models. And just on general principles, one has kind of a lot of things that come along for the right. So the arrow of time emerges via properties of normalization group flaws. You can also resolve the Horn-Big Bang puzzles, again using properties of normalization group flaws. The resolution of initial singularity becomes again something which is you can study quantitatively. It's linked to the infrared finiteness of the quantum field theory. And we have also seen an explicit resolution in the specific holographic model. So we've seen we can resolve it. Is there a hope that we can see this resolution with the data? Perhaps. I think it's a little bit too early to tell. So here I give the same formula I gave earlier. So when we did the fit, we assumed the MR is G Yang-Mills. Of course, in reality, it would be with some factor. So one needs to know the precise relation. And then that coefficient and that coefficient are kind of, I mean, if I change this MIR, I change that value. So clearly and these values only affect the very low L's. So the resolution would be imprinted in the very low L's. But of course, the low L's, they have also an uncertainty due to cosmic variance. Now, whether that's observable or not, really now depends on the details. How big is that coefficient, and what is the precise relations between the two? So if we're lucky enough, it may be in the data, or if we're not lucky enough, it would be that cosmic variance would never allow us to see exactly how the initial singularity is resolved. But that's something which is, again, it's a quantitative question now. I do my computation, and I see the numbers, and I know the error bars that we get, and I either have to further improve my numerical accuracy of how well I compute this, or I can have an a priori argument that cosmic variance is always going to be big enough. But that's something which I think can be answered in the very near future. And finally, of course, now we are living in the golden area of cosmology. The more and more data are coming in and will be coming in. Like it is expected that we would finally see tensors and non-Gaussianities within the next 10 years or so. But there is also more data from the late universe. So there is data about the large scale structure, the galaxy clustering distribution, and all of this was seeded from these initial fluctuations at the very early universe. So the statistics of the large scale structure should reflect also the very early universe. And it would be interesting to use this model. I mean, people have been trying to get, for instance, the power spectrum from early universe and see what it becomes the late universe. And it would be interesting to use also this model. Will this model tell us something about these models or not? Okay, thank you.
Thanks, Kostas, for this lecture. So we will put up the videos, and we'll also ask him to give us the slides. So we also thanks for coming.
Next, again.
Yes, again.